Welcome in EE-231 electronic devices and circuits. Keep in mind all these lectures are based on the our textbook which are using here electronic devices and circuit theory by R.L. Boylested. It's 11th edition, and in the last lecture we start from the field effect transistors. And first of all, we try to understand the concepts and compare the with the existing knowledge, which is BJTs. So bipolar junction transistors and the unipolar transistors are the FETs. This is the comparison, and there are some similarities between BJT and FETs. So there are a lot of comparison, like the input impedance and the frequency and the size and the temperature dependency, all we discuss in the first lecture. And just to understand the characteristics, we understand the operation of N-channel JFETs, and that was the starting, that was the and also the characteristics of JFET also discussed in the last lecture. Again, keep in mind it is recommended make lecture notes and then try to understand, and after reading the book try to understand the concepts and also develop in your own words. It is very important for the learning purpose. And again, in this lecture we will cover the characteristics. Construction is already covered, so we continue with the characteristics of the N-channel JFETs, and definitely we can compare at every step with the P-channel JFETs. And there are some three fundamental operation conditions for JFETs, and for we discuss for N-channel JFETs, and it will be also applicable on the P-channel JFETs. And it is related to the knowledge of it is yellow 2 1 and 2, and also try to develop the model in this lecture on specific conditions. So there are three fundamental operation conditions for JFETs. First one, when the voltage between gate and the source is 0, and if we continuously increasing the values of the voltage between drain and the source, what happens? This is the first fundamental condition. And if we change the values, in the last lecture we discussed, and we will continue from this point. And second point is when voltage between the gate and the source is with the negative reverse bias situation, and the negative with polarity. And if we, with this condition, if we fix the value of VDS, so last point will be the voltage controlled resistor, and definitely what type of resistance is affecting, and it will be the last point of the lecture. And this is the basic discussion of the last lecture. Actually we are talking about the N-channel JFETs, and if the voltage between gate and the source is 0, and it means if P is connected with 0 volt, and there is this is the whole blue color is the N channel, and on this side, on the drain side, if there is some positive voltage, then there is a reverse bias. And similarly, and this battery, if we apply some 2 volt, so when we are applying 2 volt, it means at this terminal is 0 and at this terminal is 2, difference is 2. So it is less biased in the lower portion of this junction in this depletion region, and there is more depletion region developed which is more thick, and the large depletion region on the voltage difference in the reverse bias situations. It is just like the diode and the BJT transistors. And there is some these are the ohmic contacts on the D and as well as on the S sides. And this N type material have its own resistance, and this will be understand in the form of circuits as we develop our circuits. For example, as we consider that 0 volt is here and 2 volt is here, and how this voltage is dropping across the this N type material. Actually, if we divided into further some resistors series combination, then for example, this is something which is R1 and this is R2, this is R3 and R4. So across the R4 voltage drop is, for example, have the same values, so voltage across this one is 0.5 and similarly 0.5, 0.5 and the 0.5. So there are 4.5 voltage drop across the 4 equivalent resistance if we divide. It is just to understand the concept, otherwise it is a continuous situation occur in this region. And due to this there is a current flowing is ID, and this situation can be understand definitely with this diagram. For example, if we increasing the voltage VGS is fixed, which is 0 volt, and at certain level when the these depletion regions are just coinciding, and this is the pinch off situation, and voltage applied VDS is like the pinch off voltage. And after that, if we further increase the values of VDS, then the current values is not changing, and this is the some maximum value of the resistance in this existing condition. If we change the condition, definitely resistance will be changed. So this is the discussion. It is later to the last lecture. Okay, at particular value, for example, at when VDS is increasing um, with values of VP, if we further increase the values of this pinch voltage, so what happen there is uh, a resistance of the this JFET N-channel JFET is being fixed, and it is continuously supplying the current, which is some fixed value as shown in the last graph, that current is fixed value, and this current is the IDSS. It is a saturation stage on the drain side. So drain current is equal to the at the saturation level. So it is more elaborated situations. This model, this is the equivalent model of a N-channel JFET, and this is the maximum current at the condition when VGS is 0 and when VDS is increasing further from the pinch off voltage, and IDS is the maximum current value for at that conditions. And so ignore the background noises or different type of discussion. So next one is when VGS is some negative value. So this is N type, and this contact, this portion is P type, and if we apply some voltage is, this is N channel JFETs, so it is VGS is some negative value. If we apply this VGS at this negative value, and this VDS is fixed, but it is definitely some positive value, and what happen with these situations? For the negative voltage, for example, maybe some minimum negative voltage, and there is a applied voltage between gate and the source, and for the specific are the low values of VTG. This effect is established just like the similar case when VGS is 0 at lower values of VDS. It is already discussed. So I am uh, I want to clear this situation for lower values of VGS. When VDS is some fixed value, lower fixed value, then it is a similar case as we discussed in the previous situations. And so the resulting of the negative bias and to the gate to reach the saturation level at lower values of VDS, and resulting saturation level of the drain current is reducing, and this fact will be continuing if we further decrease the values of VGS, which make the more and more negative. And this thing will be clear in this diagram, that if we further increase the values of the gate voltage, for example, this situation is occur when VGS is 0. In this case, IDSS, which is the saturation current, and in this saturation current, this is the max value in these situations. And if we further decrease the values of VGS between the gate and the source, which is somehow it is some -1, then the saturation current is lower. And similarly, if we further decrease the values, this is the current, saturation current is decreasing. So it is increasing the depletion region, and also an important point is as we divide these, there are two regions. One is the saturation region, which is on this vertical line, and if this is the pinch voltage, and after pinch voltage this region is the some saturation region. And similarly, this is the ohmic region, and we discuss this ohmic region in the next slides. And if we see that if this value is equal to, if this negative value is equal to some this negative value, for example, this voltage is equal to, if we this VGS voltage is equal to this pinch voltage, this is VDS is equal to VP, what happened? Then there is no current, and this is the lines on the horizontal axis, which showing the current 0, and this is the VDS axis applying potential, and this is the current on the vertical axis in milliamperes. So this situation is this situation is like we see the animations in the last lecture, that if there is some, for example, 3 volt and the 3 volt, each battery is showing the 3 volt, there are 3 sources of each of 3 volt, there are, so this is the something which is 9 volt. For it is being, for example, if we changing the potential across the on the gate side with some negative value, for example, if we apply this some negative -3, and this will depletion region is definitely increase, and channel will be reducing. And if we further decrease the gate voltage in a reverse situation, reverse voltage, and this will continue when we applying this potential is equal to VDS, which is equal to the some pinch voltage. So then in this situation there is no current in the source. So this is very important when there is a, if we want to block the ID drain current or somehow it is source current. So just we apply the voltage on the gate in a reverse bias situation. We are talking about the N channel JFETs. P channel, definitely these R polarities will be in opposite way we can take. So at that point there is no current. So this is the important situation. This graph shows the very important information. So this graph is divided into two important region. One is the saturation and other is the ohmic region. And this there is some control situations, and so horizontal axis is representing the applying potential, and this is the some specific potential, which is the pinch of voltage, and it is the value at when VGS is 0, as we discussed in the previous situations. But in this case we are talking about the variation of VGS with some negative values for n channel JFETs with the with the fixed values of VDS. So we are approaching at the point where VGS is -4, and this is it is equal to the magnitude value of the pinch of voltage. So in the specification sheets sometimes pinch of voltage is represented by the VGS is off, which is instead of the VP, and this is important. So region in this right hand side of the pinch of the region is typically for linear amplification. So we are talking about this region, and with the minimum distortion of the applied signals, and commonly referred as the constant current saturation, a linear amplification region. So these are the other names. Constant current saturation are the linear amplification regions. So we model this region in the last slides, and this region is defined as the constant current or saturation or the linear amplification region, whereas ohmic region is the voltage controlled resistant region. So this region is the ohmic or the voltage controlled resistance region. So there are we divide this region in and by name we are talking about the saturation region. We usually call it the constant current or the saturation region, or linear amplification region, and for the controlled portion is like the ohmic region or the voltage controlled region. So characteristics of the n-channel JFET, where drain and source are with the some ohmic contact, is the n-channel and the gate is the p-type. So characteristics of this n-channel JFET is defined here, where pinch of voltage of this particular case is -4. So this is the saturation region and it is used for the linear amplification, and this region is relevant to the ohmic resistance, ohmic or the voltage controlled region. So how we can change the resistance of the voltage with the variation of the voltage VGS. So this is very important in this ohmic resistance region. In this case JFET actually acting as a variable resistance. So this variable resistance is actually if we change the voltage, then the resistance will change, and this resistance will definitely define the gain of the control systems if we are applying somewhere for even for the amplification or some other situations. So we can control the gain by the variation of the voltage. This is the important concepts which will be applicable on the different scenarios. This region lies between the zero and the pinch of voltage. If the fabrication through fabrication, if we change the voltage of this Vp, then this region can be modified, which is on the construction or the fabrication basis. And if VGS is more and more negative, slope of the curve becomes more and more horizontal, and this is actually corresponding to the resistance value, and this thing can be verified through this relation. As we know, it is I think it is already defined, but the change in the resistance is equal to change in potential divided by the change in current. So if we decreasing further decreasing the VGS, then the resistance is increasing. For example, in this situation, if this is the change in VDS, which is always we're talking about less than the pinch of voltage, then for VGS 0, this is the change in current, and this is large change. So if there is some large change in current is here, then the resistance is lesser. For example, this is the first case. And if we are talking about the second case, about this VGS is 0, and if VGS is -2, then it is, for example, R2. In this case, where the same voltage in change, current change is relatively small as compared to the previous case. And compared to the previous case, it is, for example, this is the length representing the magnitude of change in the current, and if this length is small, then this is automatically increasing the values of the resistance, and this will be continue until we can block the current. So it is so transistor definition is fulfilled here. How to control the resistance of the JFET, and this is the N-channel JFET, and the resistance is controlled by the voltage applying between gate and the source. So in this case, we are just talking, this is the wording picked from the book. If VGS becomes more and more negative, slope of each curve is becomes more and more horizontal, which making the resistance level is increasing gradually with the decreasing of the potential between the gate and the source. And this is the important case which can be described quantitatively. So this is the important results are derived here. For example, this ohmic region, so how this ohmic region is defined, the resistance. So this is the relation which is defining the resistance at a particular value of the VGS, and this is the best approximation, and directly it is given that here R naught, it is given in the data sheet, it is the resistance when VGS is 0. So this case is given, and we are, and pinch of voltage, which is the fixed value, and it is controlled by the manufacturers, and the manufacturers can be changed this pinch of voltage. And in this case, if we change this voltage between the gate and the source, then this dynamic resistance, this becomes the dynamic resistance. and this dynamic resistance is the property of the transistor. So resistance is varying somehow, like in BJT this resistance is controlled by the base current. So in this case this current is due to the holes and electrons, whereas in this case this resistance, definitely this resistance is control the current, which is IDDS. This is the ID current, and this ID current is controlling with the variation of the voltage, and in this case there is only one type of carriers are contributing. Maybe for N channel JFET there are only electrons are contributing, whereas for P channel JFET there are holes are contributing toward this current, and this is controlled through the applying potential between the gate and the source, and this will control the resistance. For example, for the particular case we are talking about N channel JFET, if this resistance is which is given 10 kilo ohm at some VGS 0 and pinch of voltage is -6, so in this case is, so this is the R0 value which is defined at this VGS value, and also VP is also given. So if we calculate the RD with the -3, it is 40 kilo. So actual resistance is 10 kilo at VGS is 0, and if we increase the voltage between the gate and the source, this value becomes 4 times, which is 40 kilo, so at -4, and if we decrease this further -4, it will definitely the resistance of the is increasing. And if we take this VGS is equal to -6, so magnitude VP is equal. In this case there is no current, so in this case infinite resistance is there. So this is the control situation, and this control situation we can develop the amplifiers and other controlled situations. We can dynamically control these situations, and differently, directly or indirectly, we can make a controller with using these type of JFETs. And we are talking about the N channel JFETs. So similarly, all these conditions are applicable on the N channel JFETs, but sometimes there are some few characteristics or maybe change, but overall behavior of this transistor is similar to the N channel, because contribution of the current is N channel are the electrons, whereas in the P channel there are holes are the positive carriers. So this is representing the flow of the current, and channel is the path between the drain and the source. So give a comparison between the N channel and the P channel. N channel is already covered. So in the P channel, this portion which is connected by the ohmic contact through this is the drain and this is the source, and similarly this is the gate, and gate is it is substrate on the P is N type material. And polarities of the applying potential between the gate and the source in the N channel was like negative here and the positive here. This is connected to the source and this is connected to the gate. And similarly, voltage applying between the drain and the source is for the N channel is like this one. So this is the positive and this is negative. In this case, it is the reverse situations. And behavior of this P channel devices is observed here. This is the negative sign. This polarity is the representing the to measuring the potentials. So this is the VDS potentials. If we decreasing the VDS potentials, and this is the something which is the some maximum value of the VDS at max value. What happened at after that there is some breakdown situation is occur, and this is not recommended, and data sheet are alarmingly given in situations. And again, this is the small saturation region, and definitely there is a pinch of voltage is the reverse as in the N channel. And no, in this case, if VGS is 0, so it defines the some more dynamic situations of the resistance. If we further increase the values of between the of the voltage between the gate and the source, this situation is occur, and this is the dynamic resistance is greater as in the previous case. And similarly, this case is continuing. And the last case, this is the VGS for example, this numerical situation, this VGS is equal to some plus value. And for this case, this breakdown region occur in a fast way. For example, when VGS is some 0 value, this we can apply this further VDS value. And if we change the VGS from 1 to 3 or more positive, for example it is 5, so this value is like this one. So this is the threshold on the voltage of VDS. So this is the maximum negative value we can apply to for the device in a control situation or the control variable form. So these P channel characteristics is discussed for these type of situations. This pinch of voltage is +6, whereas for N channel usually in the, for example in the last case is -4 or -5 volt pinch of voltage. And this is the some maximum current which is 6 milliampere. And this situation is definitely, this lecture is very important. Maybe this is a short lecture, but definitely it will be helpful to understand the concepts in a deeper way, and try to understand the concept, develop a concept, and try to rewrite these concepts in your own words. And in this lecture we just discuss the characteristics or the operation conditions of the N-channel JFETs. And N-channel JFETs are the more are using part are the usually people are using N channel instead of P channel. As we see in the last graph that there is some breakdown situation, as definitely there is a breakdown situation, or the limits are there for N channel, but that is more appropriate values we can use. But in this situation for negative potentials is developing is and also another problem, but there is a some breakdown situations is occur at some specific values of the voltage between the drain and the source. And for so one are two key points. Keep in mind that this is a unipolar device. Bipolar junction transistor is the BJT. BJT is discussed in the last 3 or 4 chapters. This is the unipolar device, and we are talking about this unipolar device on the lower power applications like the amplifiers of and some other applications. And these FETs also have some higher power applications, maybe current of 100 amperes and 200 amperes, and sometimes we are controlling the rotation of the motors by using the 40 ampere and 50 ampere currents. So these FETs are applicable in on the large devices, electrical devices. But that case will be discussed in the power electronics. But in this electronic devices, we are usually, our target is on the low power devices. So keep this lecture, and we will continue inshallah. Next lecture will be starting with the discussion of the transfer characteristics and the and other relevant stuff inshallah. Okay, thank you so much.